Hi, in this video I will talk about electric field. Consider an object of mass m placed at a surface. So gravity will attract this object in downward direction with the force of mg. And since this object is in contact with the surface, so surface will exert a normal reaction in the upward direction. Now if we lift this object from the surface, so gravity will still be there and it will still attract it in downward direction with the force of mg. But in this case, the object is not in contact with the surface, so there will not be any normal reaction. So normal reaction was there in the first case when there was a contact between the object and the surface. While in the second case there is no contact, so normal reaction is not there. So these type of forces arise when there is a contact between two objects. So therefore these type of forces are known as contact forces. And gravity was there in the first case when there was a contact, and gravity is still there in the second case when there is no contact. So these type of forces do not require any contact. Sun and Earth are not in contact with each other, but still Sun is able to apply a gravitational force on Earth. So these type of forces are known as field forces. It was Michael Faraday who came up with the idea of field, which says that an object produces a field in the space around itself, and whenever another object comes in contact with that field, it experiences a force. For example, if I have two electrons, this electron is experiencing a force of repulsion due to this electron in this direction. But these two electrons are not in contact with each other. So the concept of field says that this electron produces an electric field in the space around itself, and since this electron is in contact with the electric field of this electron, therefore it experiences a force. So you can think of electric field, or you can think of any field, as light originating from a source. For example, if I have a bulb, so the light produced by this bulb, that is the field of this bulb, will depend on two factors. The first factor is obviously the bulb. If you take a brighter bulb, the light will be more. So it depends on the source of the field. And it also depends on the point of observation. If you take a point which is closer to the bulb, so the light, that is the field of this bulb, will be more. And if you take another point which is farther from the bulb, the light, that is the field of this bulb, will be less. So it depends on the point of observation. But it does not depend on the observer. It does not matter whether I observe it or you observe it, the light will remain the same. Similarly, the electric field produced by a charge should depend on the charge, that is the charge which produces it, and it depends on the point at which we want to find out the electric field. So suppose I have a charge Q and I want to find out the electric field produced by this charge at a particular point P. Now since this charge is the source of that electric field, because it is producing the electric field, that's why we call it as a source charge. Now in order to test what is the electric field at a particular point P, we place a charge Q at that point. So that's why it is called as test charge. Now from Coulomb's law, the force between these two charges is given by this expression, where r cap is the unit vector in the direction of r vector, and we are assuming that these two charges are positive. So that's why the force is in this direction. Now here you can see that this force depends on three factors. It depends on Q, that is my source charge. It depends on small q, that is the test charge, and it depends on the distance. But we want to have a quantity which depends on the source charge and depends on the distance. It should not depend on the test charge. So we have to somehow remove this test charge. So if we divide this force by the test charge, the q's get cancelled and we get a +1 here. So now here you can see that this expression depends on q, that is the source charge, and it depends on the distance. So that's what our electric field is. So you can say that electric field is the force experienced by unit positive charge. Why? Because here q's get cancelled and we get a +1 here. This is nothing but Coulomb's law, where we have replaced this charge by +1. So this is the force experienced by a unit positive charge placed at this point. Now since force is a vector quantity and we have find out electric field using force, so electric field is also a vector quantity. And the SI unit of force is Newton and the SI unit of charge is Coulomb. So the SI unit of electric field is Newton per Coulomb. Now let's talk about electric field lengths. As we have seen that electric field is a vector quantity, so in order to get complete information of electric field at a particular point, we have to know its magnitude and its direction. So the magnitude of electric field produced by a charge at a particular point P, which is at a distance r away from the charge, can be calculated by this expression. And since electric field is the force on a unit positive charge, so it means we can find out the direction of electric field at a particular point by finding out the direction on a unit positive charge placed at that point. So suppose I have a charge Q and I want to find out the direction of electric field at a point P. And suppose Q is positive. So we will place a unit positive charge at this point because electric field is the force exerted on a unit positive charge. And since this charge is positive, this charge is positive, so this charge will repel this charge in this direction. So it means the direction of electric field at this point produced by this charge is this. And if Q is negative, and then we want to find out the direction of electric field at this point, then we again place a unit positive charge at this point. Now since Q is negative, this charge is positive, so it will attract it in this direction. So the direction of electric field produced by this negative charge will be this. Now any vector geometrically is represented by a directed line, where this arrow represents the direction of that vector and the line and the length of this line represents the magnitude of that vector. So suppose I have a charge. This charge produces electric field and electric field is also a vector quantity, so it means we can also represent electric field by this directed line. And as we know, the magnitude of electric field is inversely proportional to the square of distance. So if we are closer to the charge, it means the magnitude of electric field will be greater, and if we go farther away from the charge, the magnitude of electric field will reduce. So the diagram of directed line will be like this. The direction of electric field from a positive charge will be like this, and if we go farther from the charge, then the magnitude will get reduced, but the direction will remain same. So here we will draw a line of shorter length because the length of directed line represents the magnitude of electric field. So this diagram will be like this. But since electric field lines represents the force on a unit positive charge, so this representation can sometimes be misleading because here you can see there are some gaps between these two lines. So it may seem that if we place a positive charge or if we place any charge on this gap, so the charge will not experience any force because there is no line. So a better way to represent this is to connect these lines. So now we have removed the gap, it means we have removed that misleading information. These arrows are again representing the direction of electric field, but now the magnitude of electric field is given by the density of electric field lines. If we are closer to the charge, then the number of electric field lines are more. The electric field lines are close together. It means the magnitude of electric field is greater. And a point farther away from the charge, these electric field lines are far apart. It means the electric field is weak. So we can draw this type of diagram for a number of charge configurations, keeping in mind some points. Electric field lines have some points which we have to keep in mind by drawing some diagrams like this. The first point is electric field lines originate from a positive charge. So if we have a positive charge, these electric lines originate from that. They are created by that charge, we say that. And they terminate at negative charge. So it means if we have a negative charge, so electric field line will terminate at a negative charge. And the second property is they can never intersect. Why? Because electric field represents the force on a unit positive charge. So if I have two electric field lines which intersect each other, and what if I put a positive charge or if I put any charge at the point of intersection? This electric field line will represent that the direction of force is this, and this electric field line will represent that the direction of force is this. But there has to be only one direction on the force on that charge. So electric field lines can never intersect each other. Now let's take a look at electric field diagrams of various charge distributions. If we have a single positive charge, then electric field lines will originate from that charge. And if we have a negative charge, they will come into that charge, they will terminate at that charge. Here we have a system of equal and opposite charge which is called as electric dipole. So here we have a positive charge and electric field lines are originating from this charge, they are coming out of it. And here we have a negative charge, these electric field lines are going inside the charge, they are terminating inside the charge. And here we have two positive charges. If when we had one single positive charge, the electric field lines were going uniformly in all directions. But here, if I allow these electric field lines to go uniformly in these directions, so they will start intersecting each other. But we know two electric field lines can never intersect each other. So in order to prevent them from intersecting, we have to bend these lines. And here you can see the repulsion between these two lines, and which also tells us that two positive charge repel each other.